Hey everybody, so we are now starting chapter 4, which is all about the atom. So we're going to start by talking about some history of the atom, how different parts of the atom were discovered, and then we're going to jump into atomic notation and atomic mass and percent abundances and some other things like that. So let's start with an atom. So an atom is the smallest particle of an element that retains the chemical identity of that element. What does that mean? That means, for example, the smallest piece of carbon you could have would be one atom of carbon. Now, we can get smaller than an atom, right? There's protons, neutrons, and electrons, but a proton from carbon would look identical to a proton from helium or gold or oxygen, because a proton is just a proton. It looks the same no matter what you put it in. So the smallest thing that would maintain a specific identity would be an atom. If you get smaller than that, the subatomic particles are identical to one another. So what we believe about atoms is really based on the discoveries of Dalton. Dalton came up with what he called the atomic theory of matter. So these are the things that his theory said. First, elements are composed of tiny, indivisible particles called atoms. The thing is, this has been modified a little bit because we know that atoms technically are divisible. Now, he was correct that that was the smallest particle that, again, retains the property of the element. If we go smaller than an atom, we don't actually have gold anymore. Now we just have a proton, a neutron, an electron. So but we did modify this a bit. So they are technically divisible. There are smaller parts than just atoms, but they are the smallest part of an element. Second, atoms of an element are identical to one another, but different from the atoms of other elements. In other words, an atom of oxygen would be the same as all other atoms of oxygen, but it would be different from atoms of carbon or gold or hydrogen. One minor thing that is different about this is that technically atoms of an element are not exactly identical to each other. The number of protons should be identical. That is literally the one atomic part. So, for example, carbon has 6 protons. If you change that from 6 protons to some other number of protons, it's not carbon anymore. So that is true that the number of protons would have to be identical no matter where I got an atom of carbon. However, the number of neutrons technically can vary. That's something called isotopes, which we're going to talk about later in the lecture. Third, atoms are not created or destroyed. We talked about this already, that they can be joined or broken apart or rearranged. So, for example, you could have oxygen reacting with hydrogen and we end up with water. But if we have 2 oxygens go in, we should have 2 oxygens come out. So the atoms themselves are not going to be created or destroyed. They're really just going to get rearranged from one another. Perhaps a compound is broken into individual elements, or elements are arranged into compounds, but the atoms themselves aren't created or destroyed. And a given compound always has the same number and type of atoms. For example, water, as we know, is H2O. 2 hydrogens and an oxygen, and that never ever changes. It will always be 2 hydrogens and an oxygen in order to be water. All right, so let's talk about those subatomic particles. I know you've learned a little bit about them before. So we've got the proton, the neutron, and the electron. Now, something I want to point out about this diagram, it's a little bit misleading. Keep in mind that the nucleus, this area here, it doesn't actually have like a membrane around it. They've kind of circled it, and it almost implies that the protons and the neutrons are like surrounded by something. They're not. They actually are just a dense, very, very dense cluster in the middle. And then the electrons are found in this area outside that is sometimes called the electron cloud. And we're going to talk, our next chapter is actually all about electrons. So let's talk about electrons first. You are responsible for having just a general understanding of these famous people, what their experiment was, and what the outcome was. You do not have to know specific details. Some of the experiments are rather complicated, but you should know in general who did the experiment, what the general findings were. So J.J. Thomson, he is actually credited with discovering the electron. He used something called cathode ray tubes, and I attached to my playlist some videos of showing how these experiments worked. I'm not going to go through huge amounts of detail here, but when he shot the particles through, and so these particles themselves, okay, so he shot this beam through here, and if there had been no plates here, so if you look at the top and the bottom, you'll see charges, positive and negative. You can actually do this with electricity or also with magnets. So if you shoot this beam through here with nothing, this beam would go straight and it would hit right here in the middle. But what he found is when he applied charges here, that this plate, when this beam passed through, it got deflected. It got deflected away from the from the negative side and towards the positive side. So it kind of hit down here instead of straight. And if he flip-flopped this and say the positive was up here, it actually would be deflected this way. And again, there's a cool video on my playlist of a teacher actually doing this with a real cathode ray tube if you want to see it. So what he basically discovered was that the particles themselves that were in this beam, they had to be negative. Why did he know that? Because like charges repel each other and opposite charges attract. So if negative charged plate caused the beam to go away from it, if it caused it to bend downward, that would imply that the beam contained something that also had a negative charge. It would be attracted towards the positive and deflected from the negative. And so in essence, he discovered electrons because electrons have a negative charge. Now, another man by the name of Millikan, his experiment is rather complicated, but he basically used this atomizer and he put this mist of oil droplets in here, and then they fell through. And he did a couple of things, but ultimately what he was able to do, he could actually figure out exactly the charge of an electron by putting charged plates here, and he also calculated the mass of an electron, and he was able to like suspend the oil drops. If he got the charge on the plates just right, this wouldn't fall down and it wouldn't go up. It would literally hover. And so it's just, all you really want to know about him is his name was Robert Millikan. The experiment is called the oil drop experiment. And mathematically, he was able to calculate the mass of an electron as well as the charge of an electron. He actually did both. And so he won the Nobel Prize in 1923 for his work. J.J. Thomson, so remember, he's the one that did the cathode ray tube experiment. So he came up with a model of what he thought atoms looked like. He called it the plum pudding model. He thought that the electrons would be like these plums embedded in this sea of positive charges. So you see how the positives and negatives were all sort of scattered throughout an atom. And so he called this the plum pudding model. And again, he came up with this based on the fact that he knew that there was this negatively charged particle. And that was, of course, the electrons. So just to get an understanding of what we know today, so look, about 2,000 electrons would have the mass of a proton. So electrons, we know that they're extremely light, and that's going to come up again later. It turns out that protons and neutrons, which we haven't talked about yet, they both have very similar masses, but electrons are much, much, much lighter. Okay, so let's talk about protons. So this famous experiment was done by Ernest Rutherford, and it's called the gold foil experiment. And again, there's a video of this, if you'd like to watch it, in the playlist that gives you a little more details about what he did. So he shot what are called alpha particles out of an accelerator. An alpha particle is a helium atom that has no electrons. So it's basically just protons is what he shot. He shot these through this very thin gold foil. Now, what he expected, he thought, because this is the model he thought was, this was Thomson's model. If this was the model, he expected that most of the beams would pretty much go straight through and strike the foil. Because the charges here were so dispersed that there wouldn't be much in there that might deflect it. Remember how with the cathode ray tubes the beam got bent. So he kind of felt like the beams would pretty much go straight. You notice they show a little tiny bit of deflection, but everything would pretty much go straight through. That's actually not what ended up happening. So here he shoots out the alpha particles, they go through the foil, and what he found was most of them went right through, some got deflected, but, and here's the real surprising part, some got bounced back. Now that should not happen if this is the correct model, because these are so dispersed that it would really be impossible for there to be enough force here to turn it the other way, okay? So what he basically discovered was the nucleus of the atom. That And if you look at this hypothesis, so here instead, let's think there's a dense nucleus in the middle. Now, most of the beams would go straight through. If they came really close to this nucleus, they would get deflected. And if they hit the nucleus, they would actually bounce back. And that matched what he saw. And he also won the Nobel Prize in chemistry in 1908 for his work. So here's his model of the atom. It's called the nuclear model. He said, atoms are mostly empty space. All the positive charge and almost all of the mass, all the heavy, dense part of the atom is in the very center. And this was called the nucleus. And it's very tiny, like a dime in the middle of a football field. So even though they kind of draw it as if the nucleus is big, like it is when you learned probably about cells last year, it's not like that. It's like giant circle, little teeny dot. The nucleus is super, super dense and very, very small. All right, so the nucleus is made of protons and neutrons. Again, there's no membrane around it. It's not like a cell nucleus. The protons and the neutrons pack super densely, and they are attracted to one another, and that makes up the nucleus. That actually stabilizes it. The electrons, on the other hand, they occupy the volume, but they're really dispersed, and they have almost no mass at all, and they're really spaced far apart, so they didn't have any effect on the beams that were being shot through. And again, this is called the nuclear model of the atom. Neutrons were discovered by James Chadwick. They never really talk much about what experiments he did, but just know that he's the one that's credited with the discovery of the neutron. And what is a neutron? A neutron has a mass pretty much equal to a proton, but it doesn't actually have a charge. So to summarize, so the actual charges, they're measured in coulombs. You don't have to know these for test purposes or anything like that. But if you can see, it's a very tiny amount of charge, positive and negative. So for simplicity, we pretty much just say that a proton has a +1 charge and an electron has a -1 charge. And then we don't put any units on that. In reality, it does have a unit, coulombs, but it's such a tiny amount of charge, it's just not convenient to work with. So that's why we stick with just a +1 or -1, and then the neutron has no charge. These are the shorthand ways of writing them. This one you tend to see a lot. Electrons, this is a very common way of writing electron in shorthand. You don't really see the neutron and proton one as often, but even when we get into chemical reactions and things, sometimes you would see electrons written this way. Now, mass. In grams, their masses are super tiny. But notice that the proton and the neutron, their masses are almost the same, but the electron is significantly smaller in mass. And so we came up with a special unit for this called AMU. And rounding these off, we basically say that a proton and a neutron each weigh 1 AMU and that an electron weighs 0 AMU. Now remember, that doesn't mean it doesn't truly have mass. It really does, right? But it's such a small amount that it's insignificant. So for purposes of chemistry, we use these units called AMU, which are going to come up a little more in a minute. So just to clarify what AMU are, AMU, they got AMU, atomic mass units, from carbon-12. Turns out carbon-12, almost all the carbon-12 that exists, or almost all the carbon that exists, I should say, is carbon-12. And carbon-12 is assigned an AMU of 12. So carbon-12 weighs 12 AMU. And it turns out that carbon-12, it has exactly 6 protons and 6 neutrons. So 1 AMU is defined as 1/12 the mass of carbon-12. So we take the mass of carbon-12 and we divide it in 12. We get 1 AMU. And since carbon-12 has 6 protons and 6 neutrons, that would mean that a proton would weigh 1 AMU and a neutron would weigh 1 AMU. And if you were to add that together, that would be 6 AMU for the protons, 6 AMU for the neutrons, and that adds up to 12 AMU, which is the mass of carbon. And so that is how we get AMU. For purposes of the test, just know that it's 1/12 the mass of a carbon-12 atom if it's kind of confusing how they derived it. And that's where we're going to stop. We're going to pick up next time and talk in more detail about the different types of atoms, the elements on the periodic table, and then atomic notation. What do all those numbers mean? There's atomic number, there's atomic mass, there's mass number, there's charges, and we can determine protons, neutrons, and electrons from those things.